my title is Pursuit and Evasion. This is an interesting part of maths, which is about, well, it's about pursuit and evasion, as you might guess. So something is trying to catch or eat or get something else, and the something else doesn't want to be caught or got or eaten by the first one. It's an area that does have many applications to real life. For example, if you're designing, say in warfare, an anti-missile system, you want your missile to knock down the other guy's missile and things like that. It's also interesting in the natural world, seeing how actual predators, like fish and so on, to what extent they use some of these strategies. But here I'm looking at it just from a maths point of view. So let me take an example to show you the kind of thing I'm talking about. So let's see if this works. I'm going to try and draw a square in green. If a green square appears up there, then it's all good. I believe you can see a green square. Good, okay. Just imagine I've drawn that by some graphics software, so it's a perfect square. Okay, so this is a courtyard in Cambridge. That's a square patch of grass. And as you may or may not know, students aren't allowed to walk on the grass in Cambridge. However, there is a student on the lawn. S for student. Okay, now, who does this annoy, or who's going to deal with this? Well, Cambridge colleges have porters. They're people with bowler hats who are in charge of discipline around the college. They want to get the student and punish the student. Of course, they also aren't allowed on the lawn. So they're on the edge of the lawn somewhere. I'll put P for porter. So there are 5 porters. Okay, and what are the rules of the game? Of course, a student could just wait in the middle forever, but then he might get hungry. So the student's aim is to get to the edge without a porter being on top of him. Okay? So the student's aim is just to get to the edge. We don't mind what happens after that. He has to get to the edge of the lawn without a porter on top of him. And what are the porters trying to do? The porters want to ensure, they're acting as a team, of course, that when the student gets to the outside, there is a porter on top of the student. Okay. Let's imagine, which may not be correct, that everyone has the same running speed. Now, you might imagine that students are, aged about 18 or 19, in the prime of life, super fit. Porters are mostly retired policemen. They're aged about 50 or above. They're less fit. But actually, porters can run pretty fast, especially if they're trying to catch a student. So let's just assume they all have the same speed. Right, so that's the game. And the question is, how many porters do you need? I'll just make some pedantic comments, which you might think, why am I mentioning them, is to avoid pedants in the audience being annoyed with me. So let me first say that in the rules of the game, there is no look ahead in the future allowed. Okay? So the student can't say, I will look in the future, work out where the 5 porters are in an hour's time, and go somewhere else. So you can't look in the future. Another thing to say is that I'll assume instant reaction times. So in my example here, if the student, say, ran like this, I'm not saying that's good or bad, the moment the student starts moving, the porters can start following if they want to. Okay? There's no reaction time or delay. Okay? That isn't quite real life, but so be it. And my third assumption is that everyone is a single point. Okay? So the rules did not say the porters win if when the student gets to the edge, there's a porter within 10 centimeters of him. The porters win if they're on top of the student. Okay, end of my pedantry bit. Oh no, one more pedantry bit, sorry. Officially, to tell you a game and ask who wins this game, the student or the porters, I will tell you the rules and the start position. And of course, the porters choose the start position, not the student. I hope we all agree with that. If the student could choose the start, then even with 1,000 porters, he'd win, wouldn't he? If the student could choose the start, I'll just draw it over here for comparison. Oh, that's thinner, that's interesting. I think it'll now be thicker, I hope. So let's go back in red. If the student was playing 1,000 porters, and we were stupid enough to say the rules are student chooses start position, then the student would probably start here. He'd put all the porters kind of around there. Whoa, I don't know how that happened. Right, it rotates. Okay, imagine that blue line isn't there. Delete. Oh, that might delete the whole... I think I'll just not delete it. Okay. Oh, wow, we're back to normal. Good, okay, did delete it. So the student would put the 1,000 porters there, and he'd just run here and win. That's a bit silly. So, of course, the official rules are that the porters can choose where everyone starts. Say, student in the middle, porters can choose where they start. And again, the question is, how many porters do we need to catch the student? So, for example, I think I'm going to another page, no? Oh, it worked. Next page. Here's an example. I hope we all agree that against one porter, the student wins. Let's try and draw it. So student in the middle. Porter is somewhere. I guess wherever the porter is, the student just says, I'll run exactly away from the porter. Does everyone agree with that? So a dotted line here, and he just runs this way. And we observe that by some geometry or something, this length here is a lot less than this length here. So the student does win. Oh, one more note for pedants. When I say the student wins, I mean if the student is sensible, he'll win whatever the porter does, right? The student could be stupid, he might run straight at the porter, but as long as the student runs away from the porter, he clearly wins. Okay, let's try 2 porters. Actually, let me give you guys about 15 seconds to think for yourself about why it's completely obvious that the student can beat 2 porters. And while you're thinking, I'll be drawing the square and the porters and stuff. Okay, so what could the student do? Against one porter, he, quote, ran away from the porter. Let's, quote, run away from both porters. In other words, let me draw the straight line between the 2 porters. And let me run at right angles away. Again, as always, ignore this slight blue box. Do you agree that while the student is running, no porter can catch him? Right, because he's running at right angles. So again, it's by Pythagoras or, yeah, you know, it's because hypotenuse is longer than wherever it's longer than. It's obviously, he doesn't get caught. And he gets to the edge and he wins. Okay, so 1 porter wasn't enough. 2 porters aren't enough. Are 3 enough? Are 4 enough? Are 10 enough? It's kind of not so clear. So let me again just pause. I'll give you guys about 30 seconds to have a think about how many porters ought to be enough. And before I do, I ought to point something out. If you say the answer is 6 porters, that's saying 2 things. It's saying 6 porters is enough, and also 5 isn't enough. If you say the answer is 3, you're saying 3 porters win, but 2 don't win. So it's 2 assertions. So give yourself about 30 seconds to have a think about how many porters we need. Okay. Well, I won't get you to vote because I won't be able to record your votes, but try and remember what you thought and we'll have a little think. Let's try and go up to 3 porters. Let's see what we can do. So we're the student in the middle. Let's see if we can beat 3 porters. Now, where are the porters starting? I want to say there are 4 sides, so there's definitely an empty side. That's not quite correct, because I guess you might say being at a corner counts on being 2 sides. So just please pretend with me for the moment that the 3 porters aren't at the corners. Okay, we'll deal with that case later. Okay, so let's just pretend that we're not allowing porters at the corners, so the porters are somewhere on the sides. We don't know where. But do you agree that because 4 is bigger than 3, which it is, there's a side with no porters on it? Agreed? So I'll draw the porters, say, I don't know, 1 here, 1 here, 1 here. Of course, it could be there are 2 on one side or 3 on one side, but either way, I hope we agree, there's an empty side. Okay. Now, what should the student do in that case? Well, pretty obvious. He kind of breaks for the border, goes straight down, doesn't he? Right, the student just runs here at full speed. Okay. And if we imagine that the side length is, let's say, 1 of this square, then this length is a half, and this length is also a half, isn't it? So the porter doesn't get there in time. Does everyone agree with that? Not even Pythagoras needed for that. Just the fact that, I don't know, the middle of a square to the middle of an edge is half the side length of a square. Okay, so that's just incredibly easy. But that was under the assumption that there were no porters at corners. Let's try the opposite extreme, where all 3 porters are at corners. What should we do now? Obviously, we shouldn't run to the midpoint of a side, should we? Do you agree? If I run to this midpoint, wow, then that porter gets me. Same if I run to this midpoint. The porter gets me. Remember, there's no reaction time. If there was a reaction time, we'd have beaten that porter, but there isn't a reaction time. So that wouldn't be okay. So we don't repeat the same thing, but it's clear what we do, right? We go for the opposite corner, we go for the empty corner, agreed? We would just run at full speed towards that corner. And do we get there first? Yes, by miles, don't we? Because the length from the center of a square to the corner is less than the side length. Because root 2 is bigger than 1 or less than 1 or something like that, but it's certainly true. Okay, just believe me. I've done the case of porters none at corners. I've done porters all at corners. Just believe me, because for the sake of finite time, the other two cases are similar. The case where there are two corners or one corner, it's similar. You always find this, you can easily run to somewhere which is either the midpoint of a side or a corner. All right. So that's shown that 3 porters isn't enough. Okay. So a good guess would be 4 should be enough. So what happens with 4? So 3 is across, 4 is question mark. I'll go back to this picture and modify it by adding a 4th porter. If I had a porter on each edge, on each side, then obviously we can't run to the midpoint of a side, can we? That wouldn't work. Equally, we can't run to a corner. Right? If these were, say, at the 4 midpoints, we obviously couldn't run to a corner. But that in no way implies the student doesn't win. All that says is if the student is stupid enough to say, I'm going to pick one point and just close my eyes and head for it and not care where the porters are, is not going to win. So if we're claiming, as I think we're probably guessing, that 4 porters is enough, the statement 4 porters is enough means we have to say how the 4 porters react to the student to always beat the student. It isn't enough to say if the student does the following obviously stupid tactics, he loses. We've got to show that the porters win by saying how they should start and how they should react. Now, there's a kind of obvious way they should start, maybe at the 4 midpoints of the edges. And there's a kind of obvious thing they should do. They should run towards the student. Right? Let's try and get close as they can to the student. Here's the trouble with that. Suppose the student would run to about here. Okay, so the student has run to kind of diagonally in from the corner. Suppose our 4 porters always chase after the student, right close to the student. Right? Then the porters would, I guess, be around here, so wouldn't they? They'd be in this region around here. Agreed? Maybe the porters are maybe we give them a little time. So the student goes there, waits half an hour without moving. The porters who are eagerly chasing the student come around here. But now, if you think about it, we can just go straight up there and win, can't we? Does everyone see that? Right. This length here is much less than going the same thing and going across. Agreed? And is much, much less than going along, round and across. So that isn't saying 4 porters don't beat the student, but it is saying that if our 4 porters just say, let's chase after the student and try as close as we can, we don't get that. That's a really important point that everyone sees. In this example here, if the student just waited near this corner until all 4 porters were there, near there, he'd run the other way and win. Or there, they'd be easy wins. So the porters are going to have to be cleverer than that. They work as a team, of course. They have to be cleverer than just saying, aim for the student, chase the student. So what could they do? Well, it's gone thin again. Beautiful, elegant left-hand side. Okay, so let's start off with the student in the middle, let's say. And the porters at the midpoints of the sides. And remember, we're trying to stop the student from escaping, we, the porters now, and what we know isn't correct is to say, let's chase after the student blindly. So what can we do? And there's a very, very elegant idea, which goes as follows. This porter here, we're going to promise that this porter is just guarding this edge. So he's the guardian of that edge. Here's what I mean by that, if we can achieve it. What I mean is that this porter promises to never leave this edge. Even if the student spends half an hour over here, this porter's still on the edge. He's going to do some stuff to ensure that maybe the student does win, but the student doesn't win on his edge. Okay? So I want this porter to do some fancy footwork to guarantee that whether or not the student wins, the student does not win by stepping onto his edge. How could we achieve that? Well, there's a kind of obvious way that the picture suggests. Initially, I'm going to dare to try another colour. Let's see what happens. Purple. Initially, the porter is at the same height or y coordinate as the student. Agreed? If the student was there on the edge, we'd want the porter at the same place, wouldn't we? So that suggests that here's what this guardian porter should do. He should just say, always stay at the same height as the student. Does that make sense? So always keep the same y coordinate as the student. So his rule is keep same. And if I write y coordinate, it sounds like it's scary maths, but height sounds unscary. Keep same height as the student. Now, first of all, is that legal? Does that involve the porter running faster than he can run? No, it doesn't, does it? I hope everyone agrees that if, I don't know, if you're in a car driving at 30 miles an hour, then your y coordinate changes by at most 30 miles an hour, right? If you're going straight up, your y coordinate changes at full speed. If you're in a different direction, it's a bit less, isn't it? So again, this is because sine or cosine is at most 1 or something. But everyone sees that. If you're running at 30 miles an hour, again, it's quite a fast speed to run, then your height is changing by at most that fast. So it's legal to tell this porter, track the student, right? He never has to go faster than he has to go. Okay. And what's the result of that? Do you agree that maybe the student wins, maybe he doesn't, but the student never wins by stepping off the lawn on this left-hand line? Right? Because at the instant when the student stepped onto the left-hand line, this porter was exactly at the same place, which is a win. Aha, great. So this porter also tracks, but on the right. This porter tracks on top. And this porter tracks on the bottom. We're done. Does that make sense to everyone? And that's a proper proof. That doesn't say we, the porters, can catch the student if he's stupid enough to ... We've shown that he always catches the student. Okay, good. So we're now experts on porter and student. But actually, this isn't the real porter and student problem, because the real porter and student problem takes place in a Cambridge court, and it's New Court of Trinity College. Does anyone know why that makes the problem different? Okay, we see lots of hands up. Is it so? Yeah, right. Okay. So it's a circular courtyard. So in the real problem, I'm afraid, it's a big circle. Same idea as before. As always, the student is somewhere inside the lawn, and isn't. Yeah, students also aren't allowed on circular lawns. Whatever the shape is, they aren't allowed on them. So here's the student. We have some porters on the circle. And our question is, how many porters do we need to catch the student? Same rules as before, instantaneous, no delay, you can't look into the future, they're single points. Again, of course, the porters can't go onto the grass themselves. So again, the porters win if, at the instant the student hits the outside, they get him. If not, the student wins. And again, it's clear that one porter isn't enough, right? Because you run away from him. Isn't it also clear that two aren't enough for the same reasons before? Here's the proof. Given your two porters, draw a line between them. And we run at full speed perpendicular to that. And then while we're running, we aren't caught, because something is perp and hypotenuse something, and we do it at the outside. Everyone happy with that? So 2 isn't enough. So how many do you need? Is it 3, because this is like a square but bent round a bit? Is it 4, because you're like a square? Is it 5? It might be 6. And 6 is an interesting number, because as I hope you know, if you take a circle of radius 1, the hexagon inscribed in that also has radius 1, has side length 1, right? You can fill in 6 equilateral triangles into the circle. So maybe that suggests 6 is the right answer. Or maybe that suggests you can't do the 6, you need just a little more, like 7. Or maybe you need 20. So I think I'll give you 30 seconds, and then I'll get you to guess and record some answers on the board. And of course, when I do that, if you already know the answer, you aren't allowed to have a guess. So give yourself 30 seconds to think about the following question. How many porters do we need to catch the student in New Court? And the answer isn't 2. I'll be erasing stuff while you're thinking. Stop you there, and let's think of some possible answers. Maybe you think the answer is 3. Maybe the answer is 4. Maybe you think it's 5, maybe 6, maybe just over 6, and then out of a box, I'll write more than 7, and it'll look like 77, but it does say more than 7. Okay, so with a show of hands, and again, if you know the answer, you can't vote. So, and I promise not to ask anyone, why do you say that? I'm not going to pick on anyone. So, hands, I think the answer is that 3 porters works. 3 people. Who thinks 4 is the right answer? Is your hand hesitating? Okay, 18 and a half. 5? Two people. 6. 3 people. 7. 7. 77, I mean more than 7. 16, okay. Okay. Well, I'm so sorry, the majority didn't get it right. The 3 isn't right, because 3 porters isn't enough. I'm afraid the 4 isn't right either, nor is the 5, nor is the 6, nor is the 7. nor is 77. In fact, no finite number works. So if you had voted in this more than 7 because you were thinking not the answer is 12, but no finite number works, then congratulations to you. So why is that? Why is it true that no number of porters works? Let me try and show you why. I'll do it for 10 porters, just to save time. You'll instantly see that what I say for 10 would also work for any number at all. So let's name the porters as P1 up to P10. Just name them for no particular reason. Here's the student in the middle. What the student's going to do is initially focus just on porter number 1. He'll do some running, some checking, some fancy footwork, maybe even make some promise, like I promise to at all later times ... But during that time, he'll just be looking at porter number 1, okay? So just think about porter P1, ignore the others for the moment. Here's what the student does. He runs down to somewhere, not too far from the edge, and he asks the following question: is porter 1 to the left of me, to the right of me, or perhaps vertically above or below me? Suppose the porter is left, for the sake of argument. Then here's what the student says. The student says, I'm going to run at right angles where I'm so far, towards the edge in the direction away from P1. So in this case, P1 is on my left, so I'm going to run right at full speed. Making sense? I hope we agree that the distance from the student now being here to the edge is less than the distance the porter would have to run. Again, some geometry stuff that says curved is longer than straight or something like that. Okay. I'm going to run this way until the distance I have left is less than 1/10, let's say, of what this porter has to go. So as an example, supposing it was 10 meters from the student to the edge point, but 11 meters from the porter, we'd run until we would say 10 centimeters away from the edge. Does that make sense? So we run until our distance to that blue dot is less than 1/10 of the porter's distance. And let's see what we've got. So time for a new picture. So it's hard to draw to scale, but still. There's the circle. Here is the student. Okay. And what we know is that this distance here is less than 1/10 of the distance from porter P1. Making sense? And now the student makes the following promise. He says, I promise that in all later running, I'll always run in a kind of cone thing like this. I'll be inside there, and I'll always be going towards the edge, never back into the circle. Okay? If he keeps that promise, then P1 didn't get him. Right? Because his time here will be almost double that or something, which is much less than the time P1 takes to get to there. Okay. So as long as we stay in there, don't do anything stupid, if we get to the edge, P1 didn't get us. Okay, so I'm going to put a tick against porter P1. Meaning, if we keep that promise, then when we get to the edge, P1 didn't get us. Okay, great. Now, let's deal with P2. In the same kind of way, what do? We run to the edge, ending up pretty close to the edge. I mean, a lot closer than a tenth of distance to the edge of our funny cone thing. And we do the same thing. We say, here we are, S. Is porter number 2 left of us, right of us, or underneath? Oh, I forgot to say, I'm so sorry, in the previous case, if the porter one was directly underneath us, left or right is fine, isn't it? Because straight is shorter than curved. So again, we say, where's porter P2? Maybe this time, P2 is above us. That's okay. Then what do? We run at right angles to where we were, towards the edge. Making sense? And again, that time to the edge is less than the porter P2's time to the edge. So we run close enough that our distance to the edge is less than a tenth of P2's distance to us. Let's try and draw this thing again. So what have we got? It's getting hard to draw, but that's okay. So here is a big piece of the arc of the circle, not to scale. Okay? At the moment, here's the student. Okay. Now, he's at some distance to the edge. And in this scale, what we're saying is that P2 is a long way this way. Right? P2 is more, this distance here is more than 10 times the little blue distance for S. Make sense? Oh, where's P1? Who cares? P1 is like 1,000 miles down the bottom. Right? We're all inside this huge, we're inside this huge cone for P1. So P1 is just way over here. It's nothing to do with our picture. Right? We're working inside this huge cone thing for P1. What do? We now say, we again promise that in all later work, we will stay in this cone here. We won't go back inwards. So we'll get to the outside. If we get to the outside, way before P2 gets to us. Okay, I can now tick off P2. And so on. Right? Each time we run till we're close, make a promise, and so on. So, for example, what happens when we deal with P3? We would run to really, really, really close, centimetre away, and we'd say, is P3 left of us or right of us? Or exactly in the middle. We'd run perp to our radius in the opposite direction until we're so close to the edge that P3 is at least 10 times as far away. Let's try and draw that. At some point, I'll stop drawing pictures. So here is, how do I draw this thing? Here's some enormous part of the arc of the circle. And at the moment, what do we have? We have that the student is about here. And then to scale, if this is, say, a meter, this is, say, 1 meter, let's say. P1 is way down here, like 100 kilometers away. P2 is way up here, 1 kilometer away. P3 is at least 10 meters away. Does that make sense? By our sequence of promises. So we again promise to stay in there. Done. Right? So all we do is we repeat this process 10 times. We are then finally in one of these. We saunter to the edge at our normal speed and we win. Does that make sense to everyone? It's quite strange. It's because a circle is curvy everywhere. With a square, that didn't work. Think about a square. In the square, when we had porter with a guiding whole edge against the student couldn't outrun the porter on that left-hand edge, could he? Remember that if the student runs, keeping y-coordinate is okay. But when it's curvy, it's always quicker to bend round. That's kind of what's going on. I don't want to say a circle is a polygon with many sides, because I don't think it is, but it's something like that. It's got more than many sides. Dominic, how long do I have? Okay. So, if you think a circle's got infinitely many sides, that's why it doesn't work, you might imagine that infinitely many porters can catch a student. can they? So I now give you porters called here's my circle. I've got a sequence of porters. They're called Mr. P1, Mr. P2, Mr. P3, and so on forever. Can they catch the student? So this will be the second last thing I talk about. And when Dominic tells me time up, I'll need 30 more seconds to talk about my final thing. Okay, so sequence of porters, infinitely many of them, can they catch the student? What does that mean to say they catch the student? It means that the instant when the student stepped out, there was a porter on top of him. Not near him, on top of him. Let me show you why the student still wins. It'll be the same proof with one extra idea. I want us all to agree with the following. If I'm in a car going at 30 miles an hour, and I'm trying to drive 30 miles, I will get there in an hour. Does everyone agree with that? You're supposed to nod. Okay. After half an hour, I haven't got there, have I? After 3/4 an hour, I haven't got there, have I? After 7/8 an hour, I haven't got there. But I do get there at time 1 hour, don't I? Everyone agree with that? It would be quite wrong to say, aha, you never get there, because at time an hour minus 1/4, you aren't there yet. And at time an hour minus 1/8, you aren't there yet. And at time an hour minus 16th, you aren't there yet. Because those limit things is 1, and at time 1, you are there. Everyone totally happy with that? You sure? And you are correct, we get there in time an hour. Put another way, if you add up on your clock the first half hour of your drive, and you add the next 1/4 of an hour, that leaves 1/4 of an hour to go. And the next 1/8 of an hour leaves an 1/8 to go. And the next 16th of an hour, and go on forever, that infinite sum isn't more than 1. Right? It equals 1, in fact. I don't even care. If you think wrongly it's 0.9 recurring, which is less than 1, that's also fine with me. All I'm saying is this sum isn't more than 1. In other words, if you're going somewhere, your distance is halving, as the time halves towards 1 hour, you get there in an hour. Right, given that, let's do our thing. We'll do the exact same process. We will start in the middle as the student. We'll think about porter P1. We'll run to close to the edge, look left, look right, go away from him exactly as before. Getting fairly close, we'll make our promise. And just believe me, that takes some time, which is, say, twice the radius. Actually, that's pretty obvious, isn't it? But I'll just say, I'll write the time it took. I'll write 2r. That means it took time at most 2r. Okay, I'm assuming we go 1 unit of time per second, so that's 2r. Everyone happy with that? And again, if I keep my promise, then that porter 1 didn't get me. Right, now repeat for porter number 2. Same idea as usual. I'll do it in blue this time. Same idea as usual. We go towards the edge, we stop when we're close, we look where P2 is, we run the opposite way, and make a little promise. Okay, I'm drawing it pretty badly, but you know it's the same picture as before. Right? So in terms of a bigger scale, I'll try and draw this bit a bit enlarged over here. Here's porter P2. Whoops, no, there's the students. I'm so sorry, there's the student. Dotted lines here. P2 is way over here, and P1 is crazy far over here. If you work out the time that took, it's much less than 2 hours, about 1/10 of 2 hours, isn't it? It's certainly at most half of 2 hours. If you check, it's the most R, certainly. So I'll put a purple R there. Meaning that took time at most R. I hope you see it's much less than R, really, isn't it? Right? This fiddle time here is about 1/10 of that time. But it's less than half of it, certainly. Okay. Tick off P2. Now do the same for P3, same process as before. Just believe if you check, it takes less than half the time. So that took time r over 2. We're now very close to the edge. Okay, so let's put all this together. If my first thing took time t1, which was at most 2r, and my second bit of moving took time at most r, and my third bit took time at most r over 2, and my fourth bit of took at most r over 4, what happens at time, add them all up? Now, this is a finite number, as you've already agreed with me, haven't you? Apart from the r, this is 1 1/2 and a third, so it's a finite number, right? It's at most, I guess, 4r. It's something finite. What happens at that exact time? Where are we? We're on the edge, aren't we? We're exactly on the edge. Because we're at most distance r from it, and at most r over 2, and at most r over 4. So our distance to the edge is 0. We're at the edge, right? So if I give you a number, a non-negative number, which is at most 1, and is at most half, and is at most quarter, and so on, it must equal 0. So we're at the edge. And at this moment, has Porter P1 got us? No. Because we were in that zone, remember? He's not even close to us. So P1 didn't get us. Did Porter P2 get us? Absolutely not. Because after our second promise, P2 didn't. We were in a zone miles from P2. So we're done. So the student wins if you have any porters. Now, I admit, at the instant he steps out, he's nearly got. I mean, P1's a kilometre away, P2 is a metre away, P3 a centimetre away, P4 a nanometre away, and so on, but no one's on top of him. Right, now my last 30 seconds, we've proved in the game of student against infinite many porters, the student wins, right? Now I'll show you that's a false statement. I'll show you that the student doesn't win infinite many porters. And then I'll leave you guys to find out what's wrong with it. So I'll show you second proof now that the student doesn't win, and I presume that at least one of the two proofs I've shown you will be incorrect. So I'm going to tell you how infinite many porters beat the student. I'll tell you how they start and how they react, how they chase and track and so on. That's what to do, right? Here's what they do. Here's the circle. I'm going to put a porter at every point on the circle. Okay? So if you like, in terms of, if you want to name them by angles, there's the center of the circle. And angle theta, I put a porter called Mr. Theta. Making sense? For every theta, so there's a porter at angle, oh, okay, I don't know if you guys are degrees or radians. I'll be degrees, I'm sorry if you hate degrees. There's a porter at angle 2 degrees. There's a porter at angle pi degrees. There's a porter at angle root 2 degrees, and so on. Does that make sense? So for each point on the circle, there's a porter. And the student starts in the middle, of course. Now I need to tell you how the porters react if the student moves. Ready? As the student moves, every porter just stands still. Do you agree the student can't win that? However clever the student is with promise this and cone that, when the student hits the outside, there's a porter there to get him. Because if he hit the outside at the point at angle 3 plus 20 pi degrees, well, rubbish, because the porter called Mr. 3 plus 20 pi degrees was there to get him, because he didn't move. So, we've shown that in the game of student versus infinite many porters in New Court, we've shown that definitely the student's got winning strategy, and also definitely he doesn't. Now, those proofs might both be wrong, that I've shown you, but certainly at least one of them is wrong. And I'll stop there, and you can work out for yourselves which one is wrong, unless they're both wrong. So that's the end.